Hello friends, today we are going to discuss the collision theory. We will take it fast. There are the four theories for the reaction rate. First one is the Arrhenius theory. Second one is the collision theory and modified collision theory. Third one is the transition state theory. It is also called as the absolute reaction rate theory or activated complex theory. And lastly, the unimolecular theory, which is given by the Lehman. The first Arrhenius theory studied the effect of temperature on the rate of reaction. Second, collision theory, which determines the rate by a collision, gives a collision frequency and energy. Then there is a need of modified collision theory where the steric factor is introduced, and the transition state theory tells how the reactant is converted into the product. And lastly, the unimolecular theory given by the Lehman, who tells us how the unimolecular reactant, that is one reactant, is converted into the product. Now, history about the Svante Arrhenius. He submitted the dissertation of 150 pages for the doctorate, and he declared as a fourth class degree. But in the defense, the third class degree is given to the respected Arrhenius, and for the same work, he got a Nobel Prize in chemistry. Okay. We know the Arrhenius equation. Arrhenius equation studies the effect of temperature on the rate of reaction given by the K is equals to A into e to the power minus EA by RT, where K is the rate constant, EA is the activation energy, which is the minimum energy for a reactant molecule to cross the energy barrier and convert it into the product. T is the absolute temperature. R is the gas constant, value is 8.314 joule per Kelvin per mole. A is the orientation factor. It is also called as the Arrhenius constant or the frequency factor. As it is before the exponential term, it is also called as the pre-exponential factor. The Arrhenius equation K is equals to A into e to the power minus EA by RT. Okay, in the logarithmic form, we will get log K is equals to log to the base 10A minus EA divided by 2.303 RT. We have already discussed this equation. It's a logarithmic form. Okay, and the graph in between log of K and 1 upon T. So this is the equation in the form of y is equal to mx plus c, where when we plot a graph in between the log of K versus 1 upon T, then slope we will get having the values minus EA divided by 2.303 R, and the intercept is log A. Again, we know the activation energy, which is the minimum energy possessed by the reactant molecule so that they cross the energy barrier and convert it into the product. Now, next, the Van Top, who received a Nobel Prize for the discovery of the law of chemical dynamics, the laws of the chemical kinetics, we can say. Now, he introduced the term like order of reaction and molecularity, and again he gives the effect of temperature and the rate of reaction. How the rate will increase by increasing the temperature. Again, we know by increasing the temperature by 10 degree, the rate may double or triple, and whatever the difference of rate, the rate in that particular temperature difference 10 degree, it is called as the temperature coefficient, which is given by the ratio of rate constant of a reaction at two different temperatures separated by 10 degree. It is given by the suppose gamma is equals to rate constant at T plus 10 degree divided by rate constant at T degree Celsius. That is the temperature coefficient. This is also known as the Van 't Hoff rule. Now, why we study the Van 't Hoff rules, the work of the Van 't Hoff and the work of the Arrhenius, because both together put forward a theory that is called as the collision theory. Again, we know the catalyst, What is catalyst? It is the substance which gives the or which shows the alternative path having lower activation energy so that reactant molecule can easily convert it into the product. Now, again, we must know about the Maxwell-Boltzmann distribution law. It gives how the fraction of molecules vary with the temperature, having that particular energy, that is having that particular activation energy. Now when we plot a graph in between the fraction of molecule against the kinetic energy, then you can see here, this is the graph, blue lines at the low temperature, red lines at the higher temperature, and this is suppose the minimum energy needed for the reaction, that is the activation energy. And if we finally look towards the kinetic energy and the fraction of molecule, then it is observed that at lower temperature, this much of fraction of molecule possess the minimum energy, that is equals to the activation energy, that is the kinetic energy. And when we lower the temperature, you can see here the fraction of molecule possessing that kinetic energy, okay, which is equals to the activation energy, will get increased, and that's why the rate of reaction will increase. Why the rate of reaction will increase with the increase in temperature? Because the fraction of molecule possessing that kinetic energy, which is equals to the activation energy, will get increased with increasing temperature. Here you can see this is the activation energy, and these are the number of molecules which possess the that particular energy. Okay, now when the temperature will get increased, you can see here the number of molecule possessing that activation energy or kinetic energy will get increases, and that's why the rate of reaction will increase. Now, next is the collision theory. The collision theory is proposed by the Arrhenius and Van Top. According to this theory, the rate of reaction is directly proportional to the number of collision per unit time. Okay, time may be in minute or second. That is, the number of collision is directly proportional. Sorry, the rate of reaction is directly proportional to the number of collision per minute time or per unit time. Okay. Now, but there are two necessary conditions, which are the colliding molecule must possess sufficient kinetic energy which is equals to or greater than the activation energy . Okay, fine. So I have disconnected for a few seconds. Okay, so according to the collision theory, it is based on the two, we can say the conditions that the colliding molecule must possess a sufficient kinetic energy which is equals to or greater than the activation energy of a molecule to cause a reaction. And second one, the reacting molecule must collide with the proper orientation. So when the two molecules get collide, it must have, means when two molecules get collide from a distance, then its kinetic energy will equals to the activation energy, so that they cross the energy barrier, and the when two molecules will get collide, okay, they must collide in the proper orientation. Now we will discuss one by one that two conditions we will discuss one by one. Now consider the reaction in between the N2 and O2. Here we will discuss that the collision, that is when the two reactant molecule will get collide, that the collision between the molecules have sufficient energy to break the bonds in between the reactant, and there is a formation of the bond in between the product. Now when the N2 and O2 will get collide, okay, there is a collision between N2 and O2, and there is a formation of the product NO and NO, then there must be a breaking of bond in between the N2 and O2, and there is a formation of bond in between the N and O. Okay, if the bond between the atoms of the reactant N2 and O2 will break, then and then only the new bond in between the NO will form. And when it will happen? When the when the kinetic energy must be sufficient to cross the energy barrier. Here you can see, okay, this blue is nitrogen and red is oxygen. You can see here, this is the blue, that is nitrogen, and red is oxygen. Nitro N2 and O2 collide with each other. This is the unsuccessful collision, and this is the successful collision. This N and this O, okay, collide. There is a formation of NO and NO. Okay, now when the two molecules will get collide, then it must collide at that collision energy is equals to the activation energy, and they must collide with the proper orientation. And when the two condition will satisfied, then that collision is called as the effective collision, and the product is formed only by the effective collision. Not all collision gives the product. Okay, the collision which satisfied these two conditions, that is the energy is equals to the activation energy and the proper orientation, will be converted into the product. That is called as the effective collision. So according to the collision theory, the rate is not directly proportional to the all collision. It should be directly proportional to the effective collision only. Okay, so according to the collision theory, in order for a reaction to occur, particle of the reactant must have enough energy and must collide at the correct angle, that is the proper orientation. Again, collision theory explains the factors that affect the rate of reaction. The greater the rate of effective collision, the greater the reaction rate. And the collision theory explains the factors that also affects the rate of reaction. So, what is effective collision? The collision in which these two conditions, as we have already discussed, that the collision in which these two conditions we can have satisfied, then that are called as the effective collision. The higher the frequency of the effective collision, the faster the reaction rate. When two molecules have an effective collision, a temporary, a high energy, or the unstable species is formed, that is called as the activated complex or the transition state. Here, consider the reaction. Suppose A plus B gives product AB. We have to consider the reaction A plus B gives product AB. Now consider the two reactants. A is there and B is there. Two reacting atoms. Suppose two A are there and two B are there. So how many number of collisions are possible? You can see here A collide with this B and this B also. It has a choice to collide with either this B or either this B. Again, this A have a choice to collide with this B or this B. Okay, as we know, these are the twice A and twice B. We get only two AB. Okay, two product will be formed if the 100% reactant, 100% product is formed. That is, okay, the twice A and twice B gives twice AB. But you can see here, the 4 collisions are possible. Again, when we add another A, again, there are the 2B and 3A. Though there are the 3A, only 2 products should be formed. Twice AB should be formed. But how many possible collisions are there? 6 collisions. Again, we add 1B. So thrice A and thrice B are there. Then thrice AB should be formed. But you can see here, the 9 collisions are possible. Means all collisions are not fruitful. All 9 collisions will not give the product, because formation of the possibility of the formation of the product is only 3. Okay, so the 9 collisions are there. Though the 9 collisions are there, the product will be, okay, will be only 3. Okay, 3 AB will be formed. So if I consider according to the collision theory, all collision gives the product. So rate should be 9. Rate of the reaction should be 9. But actually, if 100% product is formed, the rate should be 3. So when we consider all the collision, the rate calculated by the collision theory is very, very greater than the actual rate. Okay, so this is the drawbacks of the collision theory. we have to not consider all collision. So which collision we have to consider? Okay, the effective collisions we have to consider. Effective collision means what? Effective collision means what? Its kinetic energy is equals to or greater than the activation energy, and they must collide with the proper orientation. Here the beautiful pictures are there to understand the proper orientation. Suppose NO plus NO3 gives twice NO2. Okay, now this blue is nitrogen, red is oxygen. You can see here, if the collision is like this is red, oxygen, oxygen. Okay, when the collision means collision is like this, okay, it is ineffective collision because NO is not formed. Okay, nitrogen is not near to the oxygen. Okay, both are the oxygen, oxygen. In this way, again, this is the ineffective collision. Again, if the collision is like this, again, it is the ineffective collision. Again, the collision is like this, again, it is the ineffective collision. But if the collision is like this, you can see here, NO plus NO3, NO plus NO3 gives NO2, NO2. This is, we can say, the proper orientation. That is, this is the molecular orientation, and we called it as effective collision. You can see here. Now, according to collision theory, A is equals to rho into Z, where Z is the collision frequency, Z is the collision frequency, rho is the orientation probability factor. Okay, rho is called as the probability factor, okay, which represent the orientation in between the molecules, and A is the frequency factor. So this is the A, it is the frequency factor or the Arrhenius constant or the pre-exponential factor from the Arrhenius equation. Rho is the probability factor which represent the orientation during the collision of the molecule, and Z is the collision frequency. So you have to learn this equation. A is equals to rho into Z. Now, we know that when the product is formed, according to the collision theory, the effective collision gives the product only. Okay, so the effective collision, what is effective collision? Effective collision is the collision in which the colliding particle approaches each other at the proper angle and with the proper amount of energy, which gives rise the product. So there are some assumptions of the collision theory. You can see here, this is very important during when you solve the MCQs, okay, during your university examination. Okay, so what are the assumptions of the collision theory? First assumption is that the molecule are a hard sphere, because we have considered the collision in between the molecule. So when the collision is possible, when we consider the molecule as a hard sphere. Second, for a reaction to occur between the molecule, there must be a collision. At least two molecules is there. So two molecules must collide. According to the collision theory, two molecules must collide for the formation of the product. Again, not all collision produce reaction. Instead, the reaction can be if and only if the relative translational kinetic energy exceeds the threshold energy. Okay, and the Maxwell distribution of molecular velocities is maintained during the reaction. Next, a certain steric requirement should be fulfilled. We must know that we have to introduce one factor. There is one factor in the collision rate equation that is called as the probability factor or orientation factor. That is nothing but the steric factor, we can say. The rate to be proportional to the rate of the collision and therefore to the mean speed of the molecules. The collision theory of the gases gives the rate constant for a bimolecular gas phase reaction. So MCQs are there. The collision theory is applicable to, okay, it is applicable only for the bimolecular reaction which are in the gaseous phase, not in the solid and liquid. Okay, a reaction occurs on the collision of two molecules only if they possess a certain minimum amount of energy in excess to the normal energy of the molecule. Next, the collision between a molecule other than activated molecules do not lead to chemical reaction at all, and the minimum energy in excess to their normal energy, which the molecule must possess before chemical reaction on collision, is known as an equal to the activation energy. And for formation of product, 1 minute. The screen is stopped. Okay. For the formation of product, reactant molecule must collide with the proper orientation. Now, this is the mathematical expression or derivation for the collision theory. Consider the biomolecular reaction in the gaseous phase. A plus B gives AB. Now, the rate according to the collision theory is given by ZAB is equals to Na into Nb d average square into 8 pi kT divided by mu raised to power 1 by 2, where Na and Nb are the number of molecules of A and B, ZAB is the number of collision, and T is the absolute temperature, K is the Boltzmann constant, which is equals to 1.3806 10 to the power minus 23 joule per Kelvin, and K is equals to R by Na, gas constant, divided by the Avogadro number. Mu is the reduced mass, is equals to Ma into Mb divided by Ma plus Mb. D average is the average collision diameter, is equals to dA plus dB divided by 2. Now, the collision number in terms of the molar mass Ma and Mb is given by ZAB is equals to Na Nb d average square in bracket Ma plus Mb 8 pi RT divided by Ma Mb raised to the power 1 by 2. Here we take a gas constant, here we take the here we take the gas constant, here we take the Boltzmann constant. But when the number of collision calculated by this equation 2 for a reaction between H2 and I2 at this temperature 700 Kelvin, it is found that it is very, very large than the experimental value, because we consider here the all collisions, okay, because the rate is very, very high. Already we have discussed, if 3 reactant molecules are there, possibility of 100% possibility, if we consider the 100% possibility, only 3 product is formed, but 9 collisions are possible. So rate is very, very high when we consider all collisions. Therefore, in order for a reaction to occur, the collision must be effective so that its energy is equals to or greater than the activation energy, and the effective energy comes from what? The kinetic energy of the 2 reactant molecule along the line of their center at the moment of the collision. So when we consider the effective collision, we have to consider that collision which having the energy which is equals to the activation energy. So Z dash AB is equals to ZAB, that is, this is the original rate, okay, without effective collision, into minus EA divided by RT. So we know that Z dash, it is the rate. We know that what is rate? Rate is nothing but a decrease in concentration of the reactant per unit time is equals to Z dash AB. Okay, is it Z dash AB is equals to ZAB into e to the power minus EA by RT. Okay, from this equation. Now, what is ZAB? Okay, so ZAB is this from equation number 2. So we substitute the value of ZAB from equation 2, we will get this equation, that is minus dNA by dt. So this is the rate in terms of the, we can say, the number of molecules of A. Okay, but in terms of concentration, okay, so concentration of A is equals to number of atoms of A into 10 to the power minus 3 divided by Na, Avogadro number, and again concentration of B is equals to Nb into 10 to the power 3 divided by Na. So when we consider the rate law equation for this biomolecular reaction, so what is rate law equation? It is minus decrease in concentration of either A or either B. Okay, so minus decrease in concentration of A with time is equals to depend upon what? Concentration of reactant according to the law of mass action raised to power their number of mole. So minus dA by dt is equals to K2 into concentration of A into concentration of B, as one number of moles are there raised to power 1 raised to power 1. But what is the value of concentration of A? It is Na into 10 to the power 3 by Na. Okay, so we have substituted the value of the concentration of A here. So like this way, again we have to substitute the value of concentration of A here and concentration of D here. So what is cancelled? 10 to the power 3 Na and 10 to the power 3 Na get cancelled. So it is minus dNA by dt. This get cancelled is equals to K2. This Na as it is, this get cancelled. Nb 10 to the power 3 by Na. Okay, so again we rearrange this equation. So K2 is equals to what we get? Na divided by Na into Nb 10 to the power 3 minus dNA by dt. This is our equation number 7. But minus dNA by dt. Okay, so minus dNA by dt, okay, is equals to this from equation number 4. So from 7 and 4, what we get? We get K2 is equals to, this is equation 7, and we substitute the value of this, that is minus dNA by dt from equation 4. So we will get K2 is equal to this much. As it is the second order reaction, okay, the two reactants are there. So K2 is equals to unit is decimeter cube mole inverse second inverse. Now, this is the rate equation calculated by the collision theory. And again, we know that from the Arrhenius equation, K2 is equals to A into e to the power minus EA by RT. So in equation 8, e to the power minus EA by RT is there, here is there. Okay, K2 is there from left hand side, here K2 is also there from left hand side. So A is equals to this much. So A is equals to what? A is equals to this much. Okay, this much. So by comparing 8 and 9, we get A is equals to Na divided by 10 to the power 3 D average square into Ma plus Mb 8 pi RT divided by Ma into Mb raised to power 1 by 2. Okay, now when the rate is calculated for reaction in between the H2 and I2, okay, when the activation energy EA is equal to 167.4 kilojoule per mole, then A was found to be 6.010 to the power 11 decimeter cube mole inverse second inverse, and K2 is equals to 0.22 decimeter cube mole inverse second inverse, which is favorable with the experimental value. You can see here 0.064 decimeter cube mole inverse second inverse. Okay, so this is the value from this above equation, and this is the experimental value 0.064. So this may somewhat comparable when we consider the effective collision instead of all collisions. Okay, but this is valid only for the reaction simple gaseous bimolecular reaction, and for complex reaction again the theoretical value is 10 to the power 5 times from that of the practical value. So again, when we study the complex reaction using this collision theory, then again there is a need of correction because our rate is very high than actual practical value. So to compensate the theoretical value with that of the practical value, a new factor is introduced. It is called as the steric factor. It is denoted by the rho, which is inserted in the equation, and it is also called as the orientation requirement. So that why we introduce it? To compensate the theoretical value with that of the practical value. Okay, our theoretical value is very high. Okay, practical value is less. So rho should be less than 1 so that we will compensate the theoretical value and the practical value. Okay, so when we consider the collision rate is very high. When we consider the effective collision for a simple gaseous molecular reaction, rate is compensated, but still we have not considered the orientation factor. Okay, when we consider the effective collision, we consider the activation energy. Okay, kinetic energy is equals to or greater than the activation energy, and here again we have to consider, to compensate the theoretical value with that of the practical value, we have to consider the orientation requirement. It is nothing but the rho. Okay, so what is rho? Rho is the ratio of experimental value of the rate constant to that of the calculated rate constant from the collision theory.